Hello everyone. Today we will be studying linear regression and correlation. The topics we will cover are the following. We'll be studying association between variables. The variables can be categorical or quantitative in nature. We will look at how this association can be studied in terms of its direction, in terms of how closely these variables are associated with each other. Is the trend of that association linear, or it is curvy, or it has no pattern? And if the trend of this relationship or association is linear, then what is the best linear equation which can represent that association? So we will do a little review of the linear equations. Also, if you want to know how strong that relationship is, we'll be using the statistical concept called correlation coefficient. Then we'll also look at some outliers and influential observation. And finally, how good is this regression line which explains this association? So let's start with association. One of the main purposes in data analysis with two variables is to investigate whether there is an association between these variables, and can we describe that association? So we say two variables are associated if values of one variable tend to occur with the values of the other variable. So now let's look at some examples with association. For example, the amount of time spent studying for an exam and the grade on the exam. So the more you study, the better grade you get. The height and weight. Height in inches, weight in pounds. Inches of rain in the growing season and the yield of the corn in bushels per acre. A relationship between the risk and return of some stocks in a given year. Speed in miles per hour of the winning horses since 1890 in the Kentucky Derby. So these are some of these examples of our association. Now, when we are examining this association between variables, many questions come in our mind, such as, what variables are present? Are the variables quantitative or categorical? We would like to explore this nature of association. And can one variable explain the variation in the other? That leads us to the concept of a response or an explanatory variable. So now let's go and do a little more in-depth study of the response and the explanatory variables. Okay. The response variable, it measures the outcome of a study. Another name is the dependent variable. The explanatory variable, it explains the changes in the response variable. Other names are, it's an independent variable, it's the predictor variable. Very simple example, and a very common one, number of hours a week spent studying and the college GPA. Clearly, the more we spend studying, the more good our GPA would be. So, the independent or the explanatory variable is the number of hours of week studying. So this is the independent variable. And what is the outcome or the response? or the dependent variable is the collar GPA. Similarly, the effect of the amount of gasoline usage and carbon dioxide level in atmosphere. So the amount of gasoline is the same as the independent variable, because the more gasoline we use, the more carbon dioxide we are putting up in the air. So the carbon dioxide level is basically the response variable. Then the depth and the water pressure in scuba diving. We all know that the water pressure increases with depth. So in this one, we notice that the water pressure is the response variable, because we all know that the water pressure will increase as the depth increases. So the depth is the independent variable. Okay. Let's go further into this independent variable. The independent or the explanatory variable has two categories, the quantitative and the categorical. So when the explanatory variable is categorical, it defines the groups to be compared with respect to the values on the response variable. And when the explanatory variable is quantitative, it defines the change in different numerical values to be compared with respect to the values of the response variable. Okay, now let's look at some examples here. Now, in these examples, the variables, they can be explanatory of the response. They can be either categorical or quantitative. They can go either way. Okay. For example, the gender, male or female, and height. So clearly one of the variables is categorical, and height is the one in quantitative variable. Similarly, the age in years and whether or not a person has ever broken a bone, yes or no. So this 1 and 4 are associations between two different types. Let's look at number 2. It's the food type and whether it has the presence of pesticide residue over there. So clearly both the variables are categorical in nature. Looking at number 3, the temperature and the pressure of a gas, both are quantitative variables. So associations, as we just see, are of different types. But in this course, we are going to be focusing on associations between variables of the same type. Now let's look at an example. This is called an example of a contingency table. Okay, now this table summarizes the responses of 1,255 adults when asked whether they had taken the drug Prozac. So we have two variables. One is the gender and one is the taking of the drug. So both of them are categorical variables. And we get it in a table form. So the gender is being represented by the second column and the third column. One column is for males, the other is for females. Of taking of the drug, the Prozac or whatever you pronounce it, yes is the second row and no is the third row. And finally are the totals. So 531 are all the males, females are 724. So the total number of observations of the data entries in this study is 1255. Now, if you're taking the drug or not taking the drug, in that sense, if you're taking the drug, there are 132 people in the study who take the drug and 132 who do not take the drug. Total is still 1255. Okay, let's look at the question. It says, what proportion of the respondent were male? If you recall from one of the earlier chapters, we talked about proportions. What is proportion? Proportion is the number of favorable, it's the number of favorable values, or I would say the number divided by number of favorable values, or number of values which are falling in a certain category, over the total values. Okay, so what proportion of the respondents were male? The total is 1255. We write that down. And how many are male? So if you go to the second column, 531 are males. And that's our answer. That's it, 531 over 1255. Now the second question, given that the respondent is a male, so that means we are just working in the second column. All the population is males only. So that means in this one, the total values would be 531. It says, given the respondent is a male, what proportions responded yes? 36 of them out of 531 responded yes. So it's 36 over 531. Now, the next question, given that the respondent answered yes. So that means now we are going in the second row. That means looking at every person who answered a yes. So that is our whole population. That's the total value. So we write 132. It says, given that the respondent answered yes, what proportions was female? There were 96 of them who were females. And that's how questions will be coming on, association between variables which are categorical in nature. Okay, now let's look in terms of quantitative variables in association and how we represent them. One of the best ways to represent a quantitative variable is with the help of a scatter plot. And the norm is we always represent the independent or the explanatory variable on the horizontal axis and the dependent or the response variable on the y-axis. Now, if you remember from our other math classes, this is x, this is y. Okay, the main thing is the pattern. What are these? So when we get to variables, we just say, what is it telling us? If this bunch of numbers doesn't make sense, we'd plot it. Graph gives us a lot of information. So when you plot and say, oh, we see all the values are going up. These values seems to be closer to each other. They look more like a line. All these things come up from this example which is given over here. So as I said earlier, notice how all the values are close to each other, right? So you see this values between volume and temperature of a gas, how close they are to each other. Not only that, they seem to go in a straight line, these values. And also they're going up. So as the temperature is increasing, the volume is also increasing. So we can summarize what I just taught with this help of an example in the next slide. That is the pattern of a scatter plot. The overall pattern, we can describe it with the help of a trend. That means either it is linear, curved, clusters, or no pattern. For example, in the previous example, we had somewhat a graph like this. So clearly it seems linear to us. Okay. The direction talks about whether it is positive, that means whether the data points are going up, negative, they're going down, no direction, I can't see anything. So for example, this one is an example of the values are going up. Negative would be like this. And no direction, so this is negative. No direction, we'll have all over the place. There's nothing, we just don't know what's going on. It's a mess. Okay, strength. How close the points are to the trend. So here you see values are very close. Even here they are close, but here they're all over the place. Then we can look for outliers. That means when you look at this trend, so for example, let's have an example for an outlier. So I see all the values going up. And then one little value is here. And you realize, oops, what's going on? This looks like a total anomaly. That's an outlier. Okay, so we have looked at it in terms of pictures, but we're going to put this in words also. We say two variables are positively associated if high values of one variable tend to occur with the high values of the other variable, say y, or the low values of x tend to occur with the low values of y. In other words, positive association is like this. It's like data points are going up. As x goes up, y goes up. A negative association is that the variables go in opposite direction. In other words, high values of one variable will tend to occur with low values of the other variable. And when low values of x tend to occur with high values of y. So this is a negative association. So if this, clearly it says the values are going down. Now the next slide shows all different kind of pictures between this association. So the first picture clearly is a positive association because it's going up. Second one is negative. Third one, no pattern. It's all over the place. There's nothing, there is no association. Now, this one is negative, but notice how strength is, how close the values are each other. It is negative, but at the same time, the strength is very strong. Similarly, in this one, it's a positive association, but the strength is very strong as compared to the first two graphs. Now also notice we talked about the trend. A trend is what kind of a geometric figure we see. So when you look at this negative and positive, the bottom two graphs, we see, oh my gosh, it's almost like a straight line. See this one? This is almost like a straight line. Almost like a straight line. Okay, I wasn't able to make that one though, but here. Oops, sorry guys. So this is positive. Okay. You can see I can already. Okay, let me write it down nicely. This is positive. And notice it's so highly correlated. Looks more like a straight line. Yeah, now I got it better. So we all know the equation of a line y equals mx plus b. So now we're going to do that review. Now, linear equations in one variable have the form y equals a plus bx. I know we all are like y equals mx plus b, so please do not worry. Anything which is related to x and has a coefficient in the front, that is basically your slope. That's your m, remember that. And any variable on the right-hand side which has no x is an y-intercept. So here, please notice that a is the y-intercept and b is the slope, where your y is the dependent or the response variable and x is the independent or the explanatory variable. So that's the linear equation, and the slope tells us if the slope value is positive, that means the line is going up. The slope value is negative, the line is going down. All those things of a straight line will help us in our analysis here. Okay, let's look at a regression line. A regression line is a line which best fits a data set and gives us some approximate relationship between the variables. It basically means this. Suppose I have this set of data points, okay? Now, it looks like a straight line. I say, what would be the best fit? So the best fit, according to me, is, say, this line. Oh, now it doesn't make sense. It's a little off. Okay, let's try to draw a nicer line. Hopefully, I'll get it right this time. Okay. It is not working. You can guys see that. Okay, one more try, guys. Wow, this works. Okay, good. So this is called the regression line. This blue is the regression line. Okay. We're trying to fit a set of data points by something which we are more comfortable. Now I want to see what is that regression line. What we're going to do, guys. We are going to use our calculators to do the work, okay? But before we do that, let's do some more theory work. Now, the y values on the regression line that correspond to the x values from the data set are denoted by yi cap. In other words, if these are my data x values, okay? So this point dot is xi and yi. And this value is also the same, but this value, say, is this point is yi hat. That is the value which we are predicting with respect to the regression line. So as a result, you will notice there are errors because the original value is this little dot, but there's a little difference. There's a little difference here. There's a difference over here. So these are called the residuals. That means these are the errors which are associated with the original point. And the error is given by yi minus yi cap, which is basically, or hat, whatever you want to call it. That's the difference. Okay, let's look at some more, theory with slopes and y-intercepts. When we have a regression line equation given by y cap equals a plus bx, the y-intercept is the predicted value y cap when x is 0. And it is sometimes not even, we don't even get any meaningful interpretation of this y-intercept. That's okay, but we're just representing it with the help of a line, the set of data values which is given to us. Now, what does the slope do? Slope has more information. It equals the amount that this y hat changes when x increases by 1 unit. Now, when your slope is negative, the predicted y value will decrease as x increases. That means the association is negative. On the other hand, when the slope is 0, that means the regression line is a horizontal line. That means this predicted value will not change as x change. Now, finally, when the slope is positive, the predicted value y hat will increase as x increases, which in turn says that the association is positive. Okay, let's talk about residuals. Now, once we have the regression equation, we can compare the predicted values, that is given by y hat, to the actual values y to check the accuracy of these predictions. The residual is denoted by y minus y hat between the actual value and the predicted value of the response variable. Now these residuals, it measures the size of these prediction errors. A large residue means a very unusual observation. And the smaller the value, absolute value of the residual, it means closer the predicted value is to the actual value. So that means we get a better prediction. Now, let me take an example here. So suppose this and this and this and this and this, and I have some value here, and I'm going to draw a regression line like this. Now notice, let me draw this red one here so you will see much more better here. So but this is the one observation. All of the observations are closer, and these two are a little farther from each other. I'm just going to remove this little one. Okay, now look at this one. Here, notice, this is my regression line. Now, the difference between, this is the predicted value, so this is the predicted value. So this one is the predicted value. So the regression, the residual error for this point is big as compared to this. But look at this residual error. This is the predicted value if this is the x or the response, the explanatory variable. But look at this huge error. And clearly you notice compared to the rest of the values, this little value is very, very further away from the whole data values. It's like an outlier. You see that here? And that's what means a large residual indicates a very unusual observation. Now, we also talked about the strength of the relationship between these variables or associations between these variables. Now, that is given with the help of correlation coefficient. Now, correlation coefficient, it measures the direction as well as the strength of the linear association between two quantitative variables. Now, guys, this is this whole fancy formula. And remember one thing, we are not going to use these formulas. We're going to go straight to our calculator, and the calculator is going to give us the answers. Okay, now the correlation coefficient, some of the properties are, this correlation coefficient is always between -1 and 1. 1 means a very strong and a positive relationship. -1 means a very negative and a very strong relationship. And 0 means no correlation. There's no strength, no relationship. The sign of R is positive or negative. The magnitude indicates the strength of the correlationship. Okay. Some more properties. The correlation has a unitless measure. It does not depend upon the variables of the units. It doesn't even care which one is the explanatory or which one is the, response. The correlation has no issues in that. It's not even resistant to outliers. It only measures the strength. And as we said, calculating by hand is tedious, guys. We are going to use technology. Okay, let's do an example. So here we have two variables, which shows us the retail regular unleaded gasoline prices and the daily high temperatures for 4 days. The question says make a scatter plot and get the correlation coefficients. So you can easily make the scatter plot. You can have the and these are 4 values. You can just so let's look at this scatter plot if you want. So we are going to look at, so I'm going to assume my price is X, my high temperatures are Y. I'm just going to make my life easier. Okay, so price is, the minimum is 2.81, maximum is 2.88. So I'm just going to make my life simple and say 2.81, maximum, I didn't see that, 3.05, guys, sorry. So 2.81 and 2.91. I can go in 10 units, or I can go say 2.81 and eyeball the numbers, and I can do that way also. So 2.91 will not be a good because I'm going 10 units here. So let's go 5 at a time. So 2.86, 0.05. It's 0.05, 2.86. The next one would be 2.91, 2.96. Then 3 point, because we're going 0.0, so 2.96 and 05, so we would get 3.01 and then 3.06. Okay, then the temperatures are minimum is 78, highest is 92. You can eyeball it. I can say go in units of 5. So I might say, and I'll start from, not from 0. I'm going to just make a little knot. So when you make this little, twiddles here, basically it means it's not starting from origin, but we're just picking up the values we need. So here it will be, say we start with 78. We can do 78 or go in units of 2s. It's going to be too much. Do you want 4s or 5s? Okay, let's make our life simple, guys. Say 75. 80, 85, 90, 95. Okay, now, so 2.81, 78, eyeball it, somewhere in the middle. Okay, 2.86, then we have 2.97, sorry. So it's somewhere close here and it's 88. So eyeball somewhere here. Okay, then 3.05, closer here, and 92. Oops, all the way up, a little up here. Okay, 2.88. Okay, what's 2.88? Let's see, 2.88. Here, closer here, and 85. Now that number we already have, so I'm just going to eyeball the 2.88 here. Okay, so notice. So it kind of looks a straight line. Do you see that here? We would like to find out what is the, before I get the correlation coefficient, I would like to have the linear regression line. I would like to have the linear regression line. So in other words, I want to have the y hat, which is a plus bx. And as I said, we are going to use our calculators, the one variable stat. So let's get our calculators, guys, and plug in the numbers. Okay, the first thing we go to stat, edit is already there, press enter. Oh, I have some numbers in L1. Oh, we don't need that. Let's go to L1, clear, press enter. Now write down the numbers. The price goes first, 2.81, enter. 2.97, enter. 3.05, enter. 2.88, enter. Okay, now we had 4 points on the price. Let's look at the temperature. Next column, 78, enter. 88, enter. 92, enter, and 85, enter. Now we want that regression equation, and so we're going to go and click on stat, calc. We are going to look at, not here, we're going to look at linear regression, either ax plus b or linear regression a plus bx. I'm going to go to number 8, but just to let you know, guys, if you're going to use the Newton software, they're going by number 4. So if you get questions in the exams, make sure that you're using the linear regression a plus bx. That's what I will be teaching here. But to make you guys know, if you're using the Newton software, this is what they're using. So do not worry about it. So, but my lecture notes are all based on linear regression a plus bx. So what you're going to do is, we're going to take our cursor down to number 8, press enter. Now you have X list L1, Y list L2. You do not need to worry about the next two, words here because that's not what we want to focus on. We want X list, Y list. Take our cursor down to calculate and press enter. Now notice it gives you R squared, A and B. And that's what we need. So our answer is A is minus 75.206 and B is 54.98. And keep this one handy, R and R squared, because we'll be using this later on too. Or we have to also get R. R is 0.974. For some of you, if you find that you're not getting the answers, you need to have the diagnostic on. I will show you how to get the diagnostic on also over here. So let me show you that. So you go to second, if you're not getting R and R squared. So you go second and press 0, you get the catalog. And now take the cursor down till you see diagnostic. You see this diagnostic on. Press enter. There it is. Okay, so now because mine was already on, so that's why I'm getting it, but some of you will not get it, so this is what you need to do. So let's go back and do it again. Stats, Cal, and then we go to number 8. Oops, sorry guys, must have. And enter. And everything's fine. Just go to calculate, enter. So we have A and B, R squared and R. And so our answers are, for the regression equation, this one is A is negative 75.20, so negative 75.20, and B is 54.98 plus 54.98x. Okay, what was the correlation coefficient given by R? That was 0.97. It's 0.97. That means that's very highly correlated, that they're very close to each other. Look at this prices, the temperatures are very close. They're not so far off. Okay. Now, we can talk about something called extrapolation. What it means is, we want to predict the value of y using an x value which is outside the range of x values. And that's called an extrapolation. So for example, let's come back here. If I want to find out what is the temperature when the price is, say, $5. I'm like, if I use this equation, I may or may not get the right value because I'm beyond my range of the x values. My x values are between 2.8 and 3.05. So, but if I ask the question, I say, what value, what price, or what would be the temperature, what would be the temperature if the price is, say, 2.9? Oh yes, I can figure it out because it's within my range of values. Say 2.9, oh yes, I know what is it. I can use my regression line to get the value. But if I'm asking for 5, which is way back, or say 2, whereas there is no range of values, that will give me extrapolation. That's the meaning of it. Okay, let's do another example, guys. The following are the observations of classroom temperatures and mean test scores for 5 sections of Math 1530. Now we would like to find the least squares regression line with the help of calculator. And then we would ask the question, can we use this regression line to predict the mean test score when temperature is 70 degrees, 72.5 or 100 degrees? Okay, let's begin with finding the least squares regression line. That means we need to find y cap equals a plus bx. That's number 8, guys, on your calculators. Let's go ahead, plug in the values. Okay, so let's go to stats once again. enter. Now we want different values. Remember, this is now going to be temperature and L2 is going to be scores. So let's go ahead and clear the columns first before we enter values. Okay, now let's write down the temperature. Here is 69.1, then 72.3, 73.9, 74.8, and 76.6. The scores are on second column: 82, 78, 76, 74, 71. Okay, now we want to find out the linear regression equation line. Go to stats once more, calc, go to number 8. X list and Y list is L1 and L2. Then press enter and you get A to be 182.88, B to be -1, so it's a negative relationship. R is -0.99. You see an R square, don't worry, we will be coming back also shortly to this R square. Okay, let's write it down. So Y, that's the predicted regression, regression line. That's going to be 182.88. And B is -1.45x. Now R is negative. Negative means it's a negative association. And 0.99, that means it's a strong relationship, very close to -1. Okay, let's look at the next set of questions. It says, could this regression line predict the mean test score when the temperature is 70 degrees? Yeah, the minimum is 69. Yes, it is possible. 72.5, great, it is possible. But what happens when it is 100? Nope, because our data ranges, this X is the temperature, guys, remember. And by default, I'll always try to use the top line to top row, always to be my X values. Okay, so 69 and the max I was coming back was, what is the highest value? 76.6. And when you look at 76.6, 100 is far, far off. So that means if you want to find out the mean test score when temperature is 100 degrees, this means you are doing extrapolation. That's it. Okay, let's talk about outliers. We have done that earlier, but once also we like to see it from here. An outlier is a data point which lies far from the trend of the other points, and we've seen examples before. And these points typically have large residuals. So just for a reminder, so for my values are all going like this, and then I have one little value over here. That clearly is an outlier because everybody else is going, they're closer to each other, they're growing upwards, but this little line says, I'm not caring. Okay. Influential is removal from the set will considerably change the regression line. It has a large effect on results of regression analysis. Now, in order for an observation to be, influential, its value, X value is relatively low or higher compared to the rest of the data. You can see this one. And this observation is a regression outlier, falling quite far from the trend and that the rest of the data is following. Okay, but the outliers we will be talking in this course is going to be focused on, the IQR values which we have done, the interquartile range, values which are lower than the lower quartile minus the 1.5 times IQR. We are assuming, keep in mind, we're going to assume that the observations are normal. Okay. So let's come back to coefficient of determination. So I remember we talked about how good is that regression line. That means we're going to talk about coefficient of determination. What it simply means is, this coefficient of determination says the proportion of the variation in the observed values of the response variable as explained by the regression line. It basically is R squared, okay? As this has a deeper relationship with the correlation coefficient, that's why we denote the coefficient of determination by R squared, and we are not going to apply this nice little formula. We are going to use our calculators. Remember, we have seen that just a few minutes ago we had that R squared in that screen. So that's what we're going to talk about. Main question is, how do we interpret it? So if I have a correlation of 0.9, that means coefficient of determination, R squared, is 0.9 squared, which simply means that the 81% of the variation in the Y values can be explained by this explanatory variable. That's what it simply means. Okay, so going back to the problem, once again, which we just had done earlier, we like to know what is the coefficient of determination. This is the observations of classroom temperatures and mean test scores for 5 sections. And if you remember, I told you to keep that handy when we were doing this problem. A few minutes ago, the R squared is 0.988. So that's the answer to our question, which was already done earlier. So R squared is 0.988. That means 98.8% of the variation of the Y values can be explained by the explanatory or the X variable. Thank you, guys.